Come on, focus. What's wrong, little dude? What's wrong? There you are. There you are. Okay.
Alright guys, so what was R? R was 0.8 something? 808? What the hell is that? So R is definitely, this is true, check. So I found evidence of correlation. Oh, you probably wanted to see this. R is definitely bigger than 0.482. That should feel very familiar to like Z star must be bigger than 2.326 to reject a null, right? Same exact idea, just less shit to worry about writing. R is greater. Evidence. Is it weak evidence? Weak correlation. If it was 0.49, that just barely beat yeah, that would be weak as all hell. Weak positive. This is, again, this is a worksheet we're doing in class. I don't care. Decently strong, fair to middling strength, whatever the hell you want to say. Yes?
For Y, I just solved that. You don't solve that?
What do you mean? You can't solve that because there's an X in it.
Oh, yeah.
Okay. So here it would be decently strong, positive. Don't forget to tell me, this is what interpret R means. It's decently strong, positive correlation. You got to tell me if it's positive or negative. What does it tell us about the line of best fit? What do you think that means? You can tell me in a couple different ways. You can either tell me the data points are going to be decently tight to the line, or you can say, I would trust the line to make predictions. Tell me something about what this tells me about the line itself. The data points are really close to the line, or I would trust the line to make predictions, or say both of those things. If it was really weak, I'd say it's not very close to the line. I wouldn't really trust it too much to make good predictions, right? You guys see what I'm saying? One of those two things, or both of them, would really be crazy. So trust, check, data close, check. One of those two things. Maybe, flesh it out a little bit. Don't just put trust with a check mark. It's probably better. Say everything I just said a minute. Why do I say compare this to Virginia? This next question. It's 34.6% with a bachelor's degree. I want to predict the income. Why do I say compare it to Virginia? Because Virginia has that situation. How am I going to get this number? I would put money on me not getting that number. But it should be decently close because the correlation is decently strong. It should have good predictions. So for me, I didn't change mine to decimal. So I would put in here 34.6. Or you can do that thing I showed you where you go to graph, you go second count value, and you put in there 34.6, and you get your 57057. Is that what it says? Yes. I'm down in eyeball, so it's 57057 point. Don't want to forget that quarter. What should it be? What is it for real? 55,368, right? So why is it not the same? Why is it not the same? There's a lot of different ways to answer that question. Why is it not exactly equal to each other? There's other factors that didn't come into play in my analysis, right? Yeah, exactly. And since the line doesn't go through all the data points, that's a more visual explanation of why it's going to be off. I like it.
It's a prediction.
It's a prediction. It can only be so good. Let me see if you guys can handle this. Do you see how when you do this, it tells you what R squared is?
Yeah.
Stay with me now. It's kind of cool. What was R squared? It was 0.65 something or whatever. Maybe? Anybody remember what R squared was?
0.65.
Aha! Because it's just squaring that stupid thing, right? Stay with me now. This is kind of cool. You don't have to know what I'm about to say. I'm not going to ask you a question about this, but here's this. R squared is the percentage of the change in income explained by the change in bachelor's degree percentage. So 65% of the changes in income are explained by the differences in bachelor's degrees. So there must be 35% of it unexplained, other factors, right? You guys follow a little bit what I'm saying. So that doesn't mean that, again, I do have this question on here. So this seems to be one of the main variables that affect income or that relate with income, and that only makes sense, right? The higher the degree, the more people have bachelor's degree, the more money they probably make as a group. Are you somebody with me? Does that mean that somebody who doesn't have a bachelor's degree can't make much money? That's not what I said. Again, but if I have a higher percentage of bachelor's degrees in a group, I expect the average income of that group to be higher. Period. I'm not talking about any individual person. Yes?
When it says compare it to the like Virginia, how are we supposed to show that we're comparing?
Just say it's a little different but close.
So you're like not greater than or anything?
Yeah, you can totally do that too. It's greater than that, but it's close. Yeah. I got it. What was I saying? I was going to say something else. This last question. Does this mean that if you get more people to earn a bachelor's degree, then the median income of the state will increase? That's not what that means. Does it mean that it won't happen? This sounds very quantum mechanical. I have no freaking idea if it will or won't. If both. The cat is dead and alive. I love you guys. Some of you guys get that maybe?
Yes.
Cat, Heisenberg,
Yes.
uncertainty. Don't open the box. What's in the box? It's a cat. I don't know if it's alive or dead. Look it up. But, so this is not, you can't say, no, that won't happen. And you can't say, yes, that will happen. You don't have a freaking clue. Because think about it. Maybe if you make more money, you can then send your kids to college and they earn bachelor's degrees. Because you have more money to afford college. So couldn't it be kind of both ways? That kind of makes sense, like I said earlier. Bachelor's degree, you have more opportunities for jobs that kind of have higher money. But it could be a little bit the other way too. Yeah.
Is it cool if we put like not necessarily put the data points showing like one has like they
No.
have the same price but they have different?
Nope. If you go to the level of individual data points, that's drilling down too far. You never want to talk about individuals, because individuals can have all kinds of things going on. This is just talking about if I raise the percentage in the state, will the income definitely go up for the state?
Well,
And you can't say for this person, it's...
No, not per person, but like the states, like one has 22% and one has 19%.
Oh, I
The
see.
22% only makes 30.
But see, that's even still, I'm talking, because there's other factors between states, right?
Yeah.
Wouldn't one state be affected more than another state, or right? Because there's all kinds of other things going on. Is it Maine a little bit different from New Mexico? A little bit, in a lot of different areas. Okay, so I understand what you're saying, but still, that's too specific.
Okay.
Yeah. I mean, if I took Maine and I raised the percentage of bachelor's degrees in that state somehow, would the income definitely go up? No, I don't know. What's the right answer here? Yeah, we don't know. That's the right answer here. And I love it. Some of you guys are like, what the shit was the point of all this freaking shit? But isn't there a relationship for damn sure? We got a really strong R, so I know there's a relationship. So what do with that? I drill deeper with more tests, more statistical analysis. This is a surface level analysis. Why? Because this is stats 1. That's why. So of course we don't go really deep into shit. This is like a first level analysis. And they go, whoa, look at that correlation. I didn't expect a correlation. Let's go do some tests, get a little deeper on this. There are stronger tests to do for actual causation. There are causation tests. That's not what this is about. This is just a relationship test. So again, you see stuff like, as I get closer to this one water source, the percentage of people that have cancer go up. This is very Aaron Brockovich-ish, right? You know, anybody know Aaron Brockovich, that name? All right, some of you guys do. She was the one with the PG&E and the contamination of the water and the people getting cancer and so forth. So if you see a correlation between percentage of cancer victims versus distance away from something, does that prove anything? No. Does it require further analysis? Yeah. So this is very useful for seeing what to look at closer and what doesn't look like it's worth it. Right? If I get R at 0.1 on something, I'm like, I'm not gonna look at that. Yes?
So like, when would it be anything besides we don't know for that question?
If you do a test that studies causality, which is not what this kind of test does.
Stats 1, so it's always
Not
we don't
stats
know.
1.
So it's always we don't know.
Yes, for us in stats 1, the correct answer to this question is, I don't know.
Got it.
Yes. Why or why not? Because this only does correlation, not causation. So not the right kind of test to say this. So what kind of test would do that? Well, this would be a hard one. This would be a hard one to do. But if you had a state that had a certain percentage of bachelor's degrees and you notice over time they went up, then you can kind of study the incomes and see if they went up also. Huh? Yes. 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 Okay. All right. You excited? All right. So that kind of question is very easy to answer now, but the idea behind it is more complex, right? But it's still interesting, hopefully. Maybe it's, I'm used to it just being me that's interested in something, but in a room. All right. So let's talk a little bit about Chapter 11, and we'll get out of here nice and early so we can all be more ready for Friday. Johan, can you bring the... Thank you. Oh, damn it. I love it. All right, that's fine. I'm not going to talk too much about this because I didn't even bring the charts we need for this. Charts. Yeah. Yes. Everybody knows that now, like I said earlier. Chapter 11 and 12 homework is due on the day of the final because I love the name of the final. Everything for the class must be done by the final. I love that name. Everybody with me? So if I were you, I would knock 12 out because it's easy as shit. I feel okay saying that. Should be. Easy. Knock it out. And then start reading 11. There's 2 sections in 11, and one of them is really general stuff. It shouldn't be hard. Maybe. All right. So, all right, now just go with me here. All right. What governs the shape of a normal distribution? I mean, and what do I mean by that? If I said draw a normal, you guys would draw this, right? I like my little paranormal distribution. Couldn't it be this too? Or couldn't it be this? Those are all examples of normal distributions. What's the main difference between the 3 of them? Standard deviation. So what governs the shape of a normal distribution is the standard deviation. 11. You guys are with me? Now here's something. While I have this up here, let's say the mean of this one, let's say they're all mean of 10. But here the standard deviation, let's say, is 5. Here it's 3. And here it's 8. What would one standard deviation up be for this guy? 15. So what percentage would be below that? Oh shit. What would one standard deviation be up for this guy? 13. And one up for this guy? 18. Which one has the most area below? Does this one have more below 15 than this one below 13 than this one below 18? I love this question. I love this question. They're all the same. Why? Because each one of these has a z-score of 1. That's why that z-score chart doesn't give a shit what the means were to begin with, because we convert them to all the same stupid things, the number of steps away. You guys, now this is something that should have crept into your consciousness sort of maybe a little bit, but I haven't really said that directly. No, not at all? You gotta wonder, why am I allowed to use the same chart no matter what the hell? The mean is 18 billion, and the standard deviation is 48 million. And you're like, why am I allowed to use that same chart? Because they become standardized, right? They're all 1 step, 2 steps, whatever. How are you guys doing so far? Not good. Okay, I'm sorry. Shit. If I go 1 step up, doesn't matter what the mean. If I tell you what area is below a z-score of 1, can't you look that up in the chart? Somebody do that. I think it's this. We'll see if I'm right. This isn't even what I was planning on talking about, but this is still good. Everybody got that yet?
Yeah, that's it.
Yeah. 0.8413, right? All right, let me stop. Does everybody have their z-score chart? Because you guys are looking at me like I'm crazy. Look up a z of 1.00. What area is below it? 8413. You guys see that? 8413? 8413? Because those of you who didn't actually look at your chart, you're just looking at me like, wow. Look at your chart, you see. Now, for the question I just asked you, did you know what the mean really was? Because what is 1? Is that a number of dogs? Is that a... No, it's a z-score. Where would that z-score have come from? From a mean and a standard deviation. I would have calculated. Does it matter? So this picture and this percentage, doesn't that apply to each of these 3? Because isn't each of these 3, that's 1 step up. There's 1 step up, there's 1 step up. They all go here. Doesn't matter. Bless you. So in this last one, if the mean was actually 100 and it went up to 108, it's still the same stupid thing because it went 1 step up. All right, sorry. So that was all a little aside. But this is something I should have hopefully, that's why I can use that same chart for every normal distribution, because we make it all, that's what that word standardized means. I don't care what the mean and the standard deviation was. I just want to know how far something is in standard deviations. That's what a z-squared is. Okay. Coming back, Jeff. Coming back. Now, when I draw this, what does each of these represent? We don't even know. Where could that have come from? Could they all be percentages? Yes, because isn't there a z-score for a percentage? Which means there must be a picture that represents all of the percentages splayed out. They would be in a normal curve because you did a hypothesis test and used a z-score chart to do it, didn't you? Yes, you didn't even stop to think, what does that mean? That means that there must be a picture that tells me how the percentages are spread out and they're normally distributed. Why? Because NP and NQ were at least 5, right? That's the check you should have done. How are we doing so far? I really want this. The same picture would also go, of course, with means. Right? The other hypothesis test had to do with means. And for some reason, you guys didn't find S sub x bar. You just use S and S sub. Some of you guys. Okay, maybe. You guys doing all right? And this picture doesn't even give a shit about z-scores, to be honest. I did show you the formula for this, didn't I? Didn't I put the formula up there? The e to the negative x minus mu? Yes, remember that? So it exists by itself. It's just that these follow this and these follow this if they meet the requirements to be normal. All right. You're all like, great, Jeff. It's all great. So now, there's a lot of different things that follow this picture, and the chart cares about this picture, and these things work with it because they look like this. That kicks ass. But what governs the shape of this again? Standard deviation. So what if I wanted to do something like this, but all about standard deviations themselves? So instead of taking a sample and saying, you 10 people, what percentage of you like to hear about normal distribution, right?
0.
right? Instead of doing that, I would say, all right, you 10 people, what's the standard deviation of your ages? Let me go plot that. Now the other 10 people, what's the standard deviation of your ages? You guys with me? Remember when we first started talking about central limit theorem and you had to change the standard deviation? I said, this group of 10, what's your average? This group, and then we plotted the averages. Now what am I going to do? I'm going to plot the freaking standard deviations. The S for this group, and the S for that group, and the S for that group, and the S for that group. And so on. It's not going to look like this. And again, why? This is a collection of percentages or means, and the standard deviation tells me how it looks. Now I want a picture that is a collection of standard deviations. So the standard deviation can't tell me what the standard deviations look like. Does that make... Oh, I love you guys. You're all like, he's off the deep end. Does it make some sense on one level? Standard deviation tells me what this looks like. What if I wanted to make a picture of all the standard deviations? It's not going to look the same. Why? Because there's no standard deviation to talk of. It's a picture of standard deviations. So here's what's kind of cool. I know, on one level you're always like, my God, what do I actually have to do for this freaking chapter, Jeff? This is going to be not that horrible, but I must put you through the concept. Too bad for you. Okay, so this is actually really cool. If I took a normal curve and I folded it on itself, and this explains why the notation itself has a squared. It doesn't mean you take a square root. It's capturing the fundamental idea. This is why I wish I would have brought those charts, but I'm actually okay with not having done it. You can do that tomorrow. If I fold this on itself, so that means I take a z-squared and multiply it by its own self. I square it. I get the picture that represents what's called chi. Oh shit! Greek letter X. Chi squared. Not Dragon Ball Z chi. This is chi, like this. Yes. Yeah. So if you took the z-squared negative 1.89 and flipped it so it was on top of 1.89, so you multiply those together. Multiply those together. Right? That would be the chi-square for that thing. All right. Stay with me now.
Multiply them together or multiply by itself?
Yes. You multiply them together, multiply it by itself. You square it, so the negative goes away. Yeah. You square 1.89. Yeah. But that's only true for a sample of size 2. Right, now don't freak out. It's all going to be on the chart. You're not going to calculate every single thing. It's going to be very much like the t-score chart. Right? Because what's the t-score chart to? For different size samples, it tells you what the t-scores are. Right? So very similar thing's going to happen here. Now, what does this mean, though? If I do that, what's the lowest chi-square score possible then? What's the lowest number you can get when you square? No. What is... All right. What's the z-score here? Okay. What's 0 times 0? 0. I love it. All right. So that means that this distribution is not going to be symmetric. I've lost the symmetry. So it's going to go from 0 up forever. Now, for this one looks really, really freaky. It looks like this. But don't worry. Most of them are going to look like this. I don't know why I put that. This is my Jabba the Hutt graph. For sure. I know we talked about Java before, but this is definitely Java. It's skewed. Right. What was that? It's skewed to the right. I like it. And for example, I'm not going to have negative to positive. I'm not. So maybe the middle 95% for something is going to be 7.12 up to 42.98. It's not going to be symmetric because they don't have negatives and positives. I got 0 up. Okay. And again, I'm actually telling you more than normally is told to Stats 1 students. But I like to kind of show you the idea of where this comes from. There's a lot more to the story, obviously, right? But it deals basically with squaring the associated z-score. For different size samples, you're going to get bigger and bigger and bigger scores. Because there's more to it just squaring it. So it's only for a sample of size 2 that you just straight up square. Stay with me. So again, this is explaining why the chart's going to look the way it is. You don't ever have to do this yourself. Right? I always have to be sure to tell people. I tell people everything. And you don't have to be able to do this. This is just why it's going to look the way it is. All right. So in much the same way, the only thing we're going to do with ChiSquare scores, because of the time, is something called goodness of fit. So, do you remember how? Let me come at it from this standpoint. I'm only going to tell you a couple more things, then we're going to head out. Do you remember how with a normal distribution there were all these? It doesn't matter, Jeff. Different formulas, and they all went back to the same picture, right? There are all these different formulas to calculate a z-score, but you all went back to the same picture to see where it fell. So the same thing happens here. There's one formula that looks like this. So remember what I said earlier. I really want this. That's really makes sense. We've so much this semester I've talked about Florida ages, plot them on the thing, and you get this picture and blah, 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 right? So now again, I get a standard deviation, I plot it. Get another standard deviation, I plot it. So the most fundamental thing about ChiSquare is this. So here's the standard deviation of the whole population. And this is each, for every sample standard deviation I get, I can calculate a ChiSquare score. So how does that compare to the z-score formula, the basic z-score formula? What do I do for any age? I have to know the population mean age, and that can make a z-score. Well, here, what do I do for any sample standard deviation? Okay, got to know the population standard deviation, and then I can calculate a chi-square score. Do you see the connection? Maybe. I can, if I know the population mean, I can convert any data point to a z-score. Bam. That's what we're doing for most of the first part. Here, if I know the population standard deviation, for any S-score, any sample standard deviation, I can convert it to a chi-square and see where it falls on this picture. And if I have the chi-square chart, I go look up probabilities. It should feel, it's very familiar. Why is the picture so damn different? Again, that's the whole thing about the standard deviation governs this, and this is a picture of standard deviation, so I shouldn't expect it to look the same. So maybe. I know it's all very freaky. I know you're still worried about the work you're going to have to do. Here is the formula we're going to be using. That's the most fundamental formula, but we don't have time to get into using it. The one we're going to use is actually really kind of cool. Let's do this. Goodness of fit test. And what this means is, I think I have an example like this, but let me just do it up here on the board. Let me make one up. I think I have one about M&Ms. If I were to roll a die, what you got, Jeff? 60 times. How many of each face would I expect to show? How many times would a 1 show? How many times would a 2 show? Yeah, why is it 10? It's freaking 6 faces. And if it's a fair die, how many would you expect? So the expected column is theoretical. The observed column kind of makes sense as what you freaking observe, right? And nobody at home can see this shit. Come on. There you go. Hope you feel better or whatever the hell's going on. Or, just work up the gumption and come back to class. So the expected is theoretical. It's either going to be a uniform. Isn't this a uniform distribution? Because I would expect every face to show up the same amount. I don't expect it to be more 3s. Of course it's going to be more 3s. What the hell are you talking about? Right? I don't expect that. But this is a way to test to see if it is a fair die. So I expect there to be 10. Now what if I roll it and I see 6 1s, 7 2s, 5 3s, what you got, 9 4s, 6 5s, and then how many 6s do I need now? 13, 18, 27, 33. I need, holy shit, Jeff. That is really, oh well, too bad. Negative 7, negative 12, negative 13, negative 17. So it's going to be 17 over. So it's going to be 27, is that right? 33, 42, 54, 60. So let's say I see this. Now even just looking at that, would you say that this is not a fair die?
No.
Definitely not, right? But here's how this works. Let me see if you guys get this idea. What was the idea with standard deviation? I wanted to see how far each data point was away from the mean. When would it be like a 0 standard deviation? That would have to mean that every data point equaled the mean, right? So if this really was a fair die, I expect this to happen. I expect the difference here to be 0. But what is the difference?
4, 3, 5.
Yeah, 4, 3, 5, 1, 4, negative 17. So what do you think, just like standard deviation, what do you think I have to do next? Square it to get rid of the negative, right? I think I got these turned around. I always do. Officially, it should be observed minus expected, but when you square it, it's the same. Is everybody cool with that? That tells me how far off these are, but like how far are these? Are 4 off, right? What if the expected was 1,000 and the observed was 996? Is that very far off? No. But here the expected is 10, the observed is 6. That's pretty far off. It's still frickin' 4, isn't it, though? So I've got to get a relative feel for how far off it is. That's why I divide by the expected value, to see how far off relative to what I expected. So if you look at side 2, on that one sheet that has side 1, where is it? Here? The one we just did with the incomes. Goodness of fit, holy shit. Yeah, there it is. Observed minus expected. So tomorrow, so the only thing we have left, yes?
So technically that third column, or the fourth column should be negatives and the 17 should be positive, right?
Yeah, exactly. This should be turned around. But again, since I'm going to square it anyway, it almost doesn't matter. But to stay consistent, it is O minus E. That's what they picked. Yeah. So what would this have to add to be if it was perfectly what I expected? It'd have to add to be 0. Where does this picture start? 0. So to show evidence that it doesn't follow that pattern, not only do I have to not be 0, this should sound very familiar what I'm about to say, I have to not be 0 enough. I have to be far enough away from 0. And some of you guys are like, fudge. Sounds like hypothesis test. A little bit. We're not going to do all the hypothesis tests. Yes?
So in this case for the M&Ms, would they expect to be like the colors of M&Ms?
So since, we want to see if the colors are uniformly distributed, right? So therefore, how many colors are there? 6. And I've got how many total? I've got 42. So how many would I expect of each color? 7 each. 42 divided by 6. Are you guys with me? So whenever you have a uniform expectation, you take the total divided by how many categories. I really hope that makes physical sense. I don't expect any to show up more than the other, so they all have to be equal, which means you divide the total by how many categories. Is that decent? And here's what I observed, right? We actually saw 5 brown, 6 yellow, so forth. So it is different from what I expected, right? But if I do the work, it ends up that it's not that different. It's only like 3. It's only 3 on this scale. Beep. And what we got to do tomorrow is to show where the hell that number comes from. That number is like the rejection region number. It had to be at least this far away to show evidence that it didn't follow that pattern, and it wasn't. That's why I said what I did right here. We have not found evidence to reject the claim that they are uniformly distributed. It's not far enough away from all 7s. And then I'm still going to have somebody go, they're not all 7s, Jeff. Well, why is that not even coming to play? Because this is going to take every M&M in existence. It's a sample. So that's why it's got to be not just different, it's got to be some definitive amount different. So the first thing we'll do tomorrow is talk about how to, I'll bring the charts, that might help us. Talk about how to use the chart to find this, and then we'll do an example problem like this. And the rest of the time tomorrow will be devoted to review for the final. Yes?
What is the O minus E squared over E? Is that the same?
Relative difference. Right? Does that make sense? So like I was saying, if it was in the thousands, then it was 4 different. Not a big relative difference. Right? Oh yeah. These are different from 7. But how they're not relatively far away now. The sum of all their relative differences is not big enough. They have to be different. That is the number we're going to have to figure out how to look at.
I think it's more separate.
Is it far enough away from 0 means no difference at all. So to show evidence of a difference, they had to be at least this far. So they weren't that far away. Oh yeah. Thank you.